Whoa, 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 molecular geometry. We've seen water represented like this, and this, as well as this. So how do we know that water has oxygen in the middle and hydrogen on its side, but that it appears that the hydrogen is bent? Notice in all of the models, it is not a straight line, but rather bent. We will learn about this on the next couple of slides. What we already know. Our study of chemical bonds has shown that atoms will gain, lose, or share electrons in order to fulfill the octet rule. For the majority of atoms, this means 8 valence electrons, but with any rule there are exceptions. Hydrogen can be stable with 2, boron with 6, and sulfur and phosphorus can have more than 8. Chemical bonds are a careful balance between attractive and repulsive forces. We know that opposite charges attract and like charges repel. So let's illustrate that. We have our carbon and hydrogen atoms here. The like charges would be the protons within the nucleus of each, and they are repelling each other. The repulsive forces could also include the respective electrons. They're pushing away from each other. But the attractive forces, y'all, the positive and negative charges, they want to be together. So the positive charge of the nucleus would attract the electrons of hydrogen, while the hydrogen nucleus is attracting the negative electrons of carbon. And so again, like it has said, it is a delicate balance. So in order to maintain this balance, electron pairs need to be evenly spaced out around bonded atoms to prevent the bond from breaking. Let's play a little game. Predict the structure. So, rules. The black atom represents the central atom. The white atoms are atoms that will form bonds with the central atom. To form a bond, you must connect the pieces. Also, remember that each of those pieces is surrounded by electrons that are repulsed by each other. Keeping all the knowledge that you have about chemical bonds and repulsion of electrons in mind, try to form the following bonds. So for the first one, we have the central atom bonded to one atom. So these are the pieces, y'all. I'll give y'all a second to try to predict it. Good job! It does just connect to each other. This atom here is as far away from this atom here. Okay, they are evenly spaced out. Those electrons are not too close. It is the farthest it can be. Okay, let's try the next one. Central atom bonded to 2 atoms. So these are our pieces. I'll give you guys a second to predict the structure. Good. This is the structure, y'all. The atoms are located on opposite sides of the central atom. They're as far away from each other as possible. So the central atom bonded to 3 atoms. So we have these pieces. I'll give you guys a second to predict the structure. Cool deal. So the structure is like a triangle. Okay, those 3 pieces are as far away from each other as possible. Central atom bonded to 4 atoms. So these are our 4 pieces. Give you guys a second. How many of y'all actually got this? So it's a square. Well, don't forget, y'all, these molecular structures can also be 3D. So it's not limited to a flat surface. So the best structure that can form with 4 atoms around the central atom is this structure here. Yes, this is pointing up, and this is the top view, y'all. It has that triangle feature that we had before, but we simply added this fourth atom on top of it. Okay, let's learn more about these names of the structure and how we can determine them. Molecules of different substances have diverse shapes. Atoms attach to one another in various geometric arrangements, as you guys can see over here. We have our four shapes that we will learn today: linear, trigonoplanar, bent, and tetrahedral. I want you guys to note that the overall molecular shape is determined by its bond angles in 3 dimensions. Just like our intro game that we played, what is the structure? We have, to think in 3D if it calls for a 3D shape. And last but not least, y'all, I want you guys to note that the shape of a molecule is very important for its physical and chemical properties. How the molecule reacts, what it looks like, all that stuff is determined by the shape of the molecules. We have something called the Vesper theory. Vesper stands for valence shell electron pair repulsion. It predicts the molecular shape of a bonded molecule. Electron pairs on central atom, bonding and non-bonding electron pairs, repel one another, and as a result, the electron pairs remain as far apart as possible from each other to minimize the repulsion. So to illustrate this, y'all, I'm going to look at the water molecule. So this is the Lewis dot diagram of the water molecule with the shape drawn in with it. Now the different parts. So these lines are called the bonded pairs, or they're the shared electron pairs. Then these two dots that we see on top of oxygen would be the lone pairs, or the non-bonding or unshared electron pairs. So these electrons try to be as far away from each other as possible, forming this shape here that you guys see. So in this picture here, we have the lone pairs being represented by these purple, and I like to call them the Mickey Mouse ears. Hi guys! No, that sounds a little more like the gingerbread man, but you get the point. And then the shared pairs would be the bonds we see here. So bonded electrons. Shared. Continuing on with this, y'all, lone pairs and bonded pairs. The repulsion of lone pair electrons only on the central atom is greater than the repulsion of bond pair electrons. But why? So this is an illustration of a bonded pair. The electrons are being shared between X and H. And again, this is the model for it. We see that a bonding pair is shared between two nuclei, and the electrons can be close to either nucleus. They are relatively confined between the two nuclei, so again, not much room, y'all, to move about. Could be close to X, could be close to H, but again, this is its confined area, not much space. But a lone pair is localized only to one nucleus. So the two electrons can't move about in this entire region here. Okay, so the lone pairs electrons can move within this space. The model version of the lone pair, again, the Mickey Mouse ears, represents this big area, y'all. So it's illustrated there. Now, let's talk about the strength of these repulsion. the greatest strength would be lone pair to lone pair. So again, these guys, two of them would be pushing each other away the strongest, strong repulsion. Then the next one would be between a lone pair and a bonded pair. Remember, the bonded pair is very, very, very localized, so it doesn't have a lot of room, doesn't repel as much. And last but not least, y'all, the bond pair to bond pair, least repulsion. Applying the Vesper theory. Step 1. We must draw the Lewis-Dot diagram of each of the elements in the molecule, with the least electronegative in the center. Why is that? So again, the least electronegative element has the tendency to let go of its electrons. They share them, okay? Whereas the one that has high electronegativity, those nucleus, again, wants to attract those shared electrons closer to it. So it would be considered a terminal atom. So the least electronegative in the center, to recap. Step 2, determine the number of bonded and lone pair electrons on the central atom. And step 3, arrange the atoms around the central atom so electrons are as far away from each other as possible. So step 2 is the crucial step that determines the shape. And I'm going to be recapping this throughout the lecture. Okay, so step 2, determine the number of bonded and lone pair electrons on the central atom. Okay, so that is the crucial step. Linear. So it's two atoms attached to a center atom. And then it could also be just between two atoms as well. It has 0 unshared pairs or lone pairs on the central atom. Like I said in step 2, the central atom, we need to determine the number of bonded and unshared pairs or lone pairs. And that actually determines the shape. The bond angle is 180 degrees. And our example is beryllium difluoride. And so to draw the structure, we draw it like so. And I'm going to note the bond angle. You guys don't have to. I'm going to do it in a different color to show you guys it's not part of the shape. So it's 180. Bent. So bent is two atoms attached to the center atom, similar to linear, but it has two lone pairs on the central atom. The bond angle is 104.5 degrees. And our example would be water. So to draw this out, y'all, again, I'm going to draw it like so. And then I'm going to note the angle here. Trigonal planar. 3 atoms attached to the center atom. 0 lone pairs on the central atom. The bond angle is 120 degrees. And our example is aluminum fluoride. So how do we draw it? Again, I am going to draw it like so. Similar to a triangle, y'all. The bond angle, I'm going to be labeling it. Again, 120 degrees. Tetrahedral. 4 atoms attached to the center atom. There's 0 lone pairs on the central atom. The bond angle is 109.5 degrees. And our example is methane. So how do we draw it? I draw the central, and I add the one on top, add, again, the legs here, and a short leg pointing back. The angle would be 109.5 degrees. So this is a summary page of all the shapes that you guys have learned, and it depends on the number of lone pairs and the number of atoms attached to the central atom. So when I say let's analyze, I mean let's take a look at the central atom and see what is happening there. So if I take a look at the linear shape, I see that there are two atoms attached to it with no lone pairs. This one has three atoms attached to it, thus it's called trigonal planar. Now, if I take a look at this one with one lone pair, it has two atoms and one lone pair attached to it, so it would be considered bent. Then finally, I have my last shape with no lone pairs, but four atoms attached to it. It's called tetrahedral. And if I have two lone pairs attached and two atoms attached to it, this is considered to be bent as well. Let's look at what the wedges and dashes mean. This is to represent 3D structures in a 2D sense. So the wedge, and I'm coloring in the wedge, and it looks like a colored in triangle. This is a wedge, and it means going out of the paper. The dashes means going into the paper. Going in and out of the paper. What does that all mean, Mr. Tran? Very good question. It tries again, like I said, to represent a 3D structure. So this wedge simply means that this X right here, I'm going to draw in purple, is popping right out at you. Okay, if we were wanting to visualize this in a 3D sense. Whereas the dashes here means that it's pointing away from you, okay, into the paper, away from you. Hopefully that clears it up. And again, this is just a summary of all the shapes you've learned today. Predict the shape of CO2. So, the first thing we should do is always to draw the Lewis dot diagram. And that's what I have right here. So I take a look at the central atom and see how many atoms are attached to it. So I'm going to be analyzing that. I see that I have two attached to the center, no lone pairs. This means I can look at my notes and I see that the only one that fits the description would be linear. So linear is right. It is a straight line. This is linear. Okay, bond angle would be 180 degrees. Okay, the next one, y'all, HCN. So that's the Lewis dot diagram. Again, I take a look at the central atom and I see that there are two atoms attached to it, no lone pairs. So this would be linear as well. And I can see that it does form a straight line. Let's look at the model. Boom, we are right, a straight line there. So let's predict the shape of methane and water using the Vesper theory. So for methane, we need to draw the Lewis dot diagram first. So it is carbon with 4 hydrogens attached to the center atom. So if we take a look at our notes, the only one that has 4 atoms attached to the center with 0 lone pairs is tetrahedral, and we see that here. The shape can either be represented with those wedges and dashes that I showed you on the previous slide, or with this model here. Okay, you can draw either or, either one is acceptable. Now, for water. Water has one oxygen atom and two hydrogen. It has two lone pairs on it as well. So if we take a look at our notes again, two lone pairs, two atoms attached to it, has a bent shape. So we see that there is bent, and we have the 3D models that we can draw to represent it. Now you try. We have boron trichloride, we have hydrosulfuric acid, and chloromethane. So determine the shape. The solutions to these problems will be located on the next slides. Okay, so for boron trichloride, I'm going to be drawing out the Lewis structure. Remember, the shortcut method is just to try to draw the valence electrons first and connect the dots. So boron has 3 valence electrons. I see I have to have 3 of them around boron, 3 Cls because there are 3. Then chlorine has 7 valence electrons. So I'm going to draw those 7 valence electrons first. And notice I'm placing them one at a time around in clockwise fashion. So now the single dots are the ones that create the bond. So single, single, it makes a bond. Single, single, makes a bond. Single, single, makes the bond. So that doesn't look like the structures that you have seen in the notes. So I always redraw it to make it look nice. So B is in the center, and I know that again it has 3 around, and I'm going to draw the valence electron, the lone pairs real quick. And there we have it. So let's analyze. I take a look at my central atom and see how many atoms and lone pairs are attached. So I only see 3 atoms, so I'm going to be writing that down. 3 atoms attached, y'all. Okay, so 3 atoms attached. No lone pairs. I take a look at my notes, y'all. That is trigonal planar. So I can draw it many ways, and the 2 ways that we have so far. We have B with Cl attached to it in the same plane. No popping out, no going into the paper. And I can also represent it as this model here. Now for hydrosulfuric acid. First thing I'm going to do is draw the Lewis dot diagram. Valence electrons first, y'all. Sulfur has 6, hydrogen has 1. The single dots create the bond, single dots create the bond. Doesn't look like anything we've seen before, so I'm going to be redrawing it out to make it look nice, but don't forget about the lone pairs. Now, let's analyze. Again, around the central atom, I have 2 atoms attached and 2 lone pairs. Taking a look at my notes, y'all, the only one that fits this description would be bent. So I can draw it in many ways. I'm going to start off with the letters and then my lone pairs here. And then I'm also going to draw the spherical one. There we have it. Now for the chloromethane. I'm going to be drawing out the Lewis dot diagram. Carbon goes in the middle. I have 3 H's. Doesn't matter which order I put it, and a Cl. Then valence electron time. Carbon has 4, hydrogen has 1, and chlorine has 7. Single dots gets the bond. Single dot, bond, bond, bond. Doesn't look like anything we've seen before, so again, I redraw it. Anything that creates a bond, I'm drawing that bond in. Hydrogen here, hydrogen here, hydrogen here. Chlorine here, and its lone pairs. Let's analyze. I take a look in the middle. I see that there are 4 atoms attached, no lone pairs. So the structure is tetrahedral. Drawing my shape, either I draw it with my elements visible. Drawing my elements invisible, or not visible. Too many, so I forgot my CL. There you go. And the shape here. So there you have it, y'all. Okay, you've reached the end of the problems. Have a good one.